Okay, ladies and gentlemen, thank you for staying. In the last talk of today, I would like to bring back the focus from the Agulhas region back to the global, maybe not the global, but at least the Atlantic large-scale perspective. We've seen in a couple of talks, especially this morning, kind of these conveyor belt schemes and all. Of course, every speaker emphasized that this is a highly idealized case and emphasized that mesoscale eddies and variability are much important for the ocean circulation. And this is especially true for one of the choke points for the Atlantic thermohaline circulation, as the previous speaker, Monsieur Hureau, pointed out. And I will not introduce again you to the Agulhas region, but rather emphasize the fact that I would like to do the spits between the high resolution, the complicated nonlinear dynamics in the Agulhas region, and the large scale, more gradual and decadal variations. So the outline of my talk is, after some more slides of introduction, I will show you how we modeled the Agulhas current, especially the embedding into the large-scale circulation. What we mean with Agulhas leakage, it was mentioned a lot of times, but what do we really understand as Agulhas leakage? And then show you two large-scale responses, one wave response acting very fast to the North Atlantic, one more gradual advection response, and then, of course, some sort of summary. Now, I thought it would be a good idea to put up that figure because that's one of the famous papers of our host. But it's also showing that the Agulhas is not only sandwiched between the Indian Ocean and the Atlantic, but is also adjacent to the Southern Ocean. And the Southern Ocean, or the gradient from the Agulhas to the Southern Ocean, is not only a temperature gradient, it's also a gradient in terms of nutrients. And this is emphasized here by a satellite picture showing ocean color mainly being a synonym for ocean productivity. And the color and the temperature is visible in a series of oceanic fronts attached and bounding north of the Antarctic circumpolar current. And these oceanic fronts, which are important for, as I say, for biological activity, are used as a synonym for global variation in climates by the paleo community. And I would like to show you one more slide of the paleo before I will then concentrate back onto the decadal timescale. This is a series of paleo timescales which has been published separately in individual manuscripts that shows the global embedding of the Agulhas and the importance of the Agulhas circulation in the large-scale perspective. And I'm not an expert on that, but I think I'm able to guide you a little bit through by emphasizing certain points. And one of these fronts, the subtropical front, which basically separates the Agulhas region from the Southern Ocean, has been shifted south back in time. Time is going from right to the left. So every time the southern subtropical front shifts south, the SST increased. That's basically what Mathieu showed before as well. The Agulhas leakage peaks, is high at that time. And then we see the global perspective. This is also the same time when the ice volume decreases. And the ice volume decreases not before the Agulhas leakage peaks, but more or less at the same time or slightly afterwards. And also is an indicator for the strengthening of the MOC. So it has been emphasized by a lot of scientists that the Agulhas leakage is capable of not only stimulating the MOC, the Atlantic MOC, but also kick-starting the MOC. Now, what is the motivation or the driving force for that? Of course, subtropical front is not a driving force. It's rather a synonym for for a certain climate or a certain climate gradient. And it has been pointed out before that, of course, you need winds to drive oceanic currents, wind changes. And what has been brought up so far is the importance of the trade winds, and this is only showing the zonal component. Of course, you have trade winds at an angle there. And I would also emphasize you to the fact that, of course, this is a combined system, a combination of the trade winds and the westerlies. Now, in the past, it has been emphasized that the wind fields were shifted northward. For example, at the last glacial maximum, at every cool times, the winds have been shifted north. So did the tropical fronts. This is where the Paléoclimatology took place and sampled biological productivity, and that the Agulhas current was reduced and the Agulhas leakage was at least minimized, if not shut down completely. On the contrary, if the wind fields shift to the south, and in this case I rather mean the southern hemisphere westerlies, as it happened during warm times and as it is happening during these anthropogenic climate change, subtropical front shifted south, the Agulhas current has a wider gap, so to say, to flow into the Atlantic. And I will emphasize that and demonstrate by our modeling perspective how that works in detail. Now, what happens if you bring more water to the Atlantic? So what's the effect? And of course, we have some evidence for that from the literature so far. More than 10 years ago, Wilbert Dwyer started a first approach by using a model. And of course, 10 years ago, the models were not capable of simulating the nonlinearity of Agulhas leakage. So what he did is artificially bringing heat and salt from the Indian Ocean to the Atlantic. So he basically, in the model, shifted temperature and salinity from the Indian Ocean to the Atlantic, and then studied the long-term evolution of the Atlantic MOC. And by doing that in some long-term runs, so this is now kiloyears, 10,000 years, he gradually increased the Agulhas leakage up to a certain value and decreased it again. The North Atlantic deepwater production, basically the main, one of the main driving forces for the Atlantic MOC, further north, more or less linearly followed the Agulhas leakage on that timescale. From time to time, however, he saw very abrupt shifts, both in the increasing phase, but also in the declining phase. And these abrupt shifts were caused by decadal variability, where the salt and the temperature gradually moved from the leakage area towards the north, and then had an impact on the convection region. It was mainly the salt, because the temperature, the heat, the excess of heat is rather quickly lost to the atmosphere. It was rather the salinity that made the way to the north, acting as a density increase and therefore acting as an increase for the deep water production there. And quite recently, we have seen some other evidence for the importance of the Agulhas leakage. This is shown in a climate model by Lee et al., a Miami group, that tried or that did use an ocean-only model, which was forced by atmospheric data from a climate model. Climate model, which is the green one, a climate model of the past 100 years or so, that basically was able to follow and to simulate the rise in the Atlantic heat content, in the North Atlantic heat content, nicely following the observations. Now this, using that, they tried to separate it and made two different experiments. One was using the forcing, the anthropogenic forcing only in the Atlantic Ocean, and the other one was only driving the anthropogenic forcing outside the Atlantic. And only the model outside, with the anthropogenic forcing, atmospheric forcing outside the Atlantic, this is the red curve, was able to follow the full trajectory, was followed to follow the observations, whereby, in contrast, the model with a local effect in the Atlantic alone was not able to explain the rise in the Atlantic Ocean heat content. And of course, as you would know, because otherwise I wouldn't brought it up, these anomalies came through Agulhas leakage, came through an increase of Agulhas leakage. Now, all these models from a paleo, but also to the climate model perspective, of course, are coarse resolution models. And we've seen, especially by the previous speaker, that the Agulhas current region is highly nonlinear. There is no steady flow from the Indian to the Atlantic Ocean. It's rather a series, a highly complicated series of eddies. And these eddies are massive. These eddies reach down to the ocean bottom, have a diameter of 200 to 300 kilometers, are the largest eddies in the world ocean and also the long-lived eddies in the world ocean, with lifetimes of more than 2 years on the way from say, Cape Town to South America. But they are still eddies. And eddies with a 300 kilometer grid scale easily fall between the grid cells of a coupled climate model at 2 degree or even 1 degree resolution, not to speak of any paleo model. On top of that, we have another mesoscale variability, and we've also seen that the importance of the mesoscale eddies in the source regions. We have mesoscale eddies called Mozambique eddies in the Mozambique Channel that are caused there by barotropic instability. These eddies flow towards the Agulhas, merge with eddies east of Madagascar, and in a very complicated process, by pulsating, meandering effects, they strongly interact with the Agulhas current. They interact with the Agulhas current in a way that they shift the Agulhas current up to 100 or even 200 kilometers offshore, and rather cause disruptions on its way to the south. Now, how did we do the splits now between modeling the Agulhas current at high resolution, that the necessary nonlinearity, high resolution, but also the embedding in the large-scale circulation? For this, we used a nested ocean model, and I must say that this is a complete French system, because it consists of a formerly French model, now European model, in a French, German, British collaboration, and also using a French nesting technique. So it's a completely French system in that sense. So we basically use the combination of a high resolution nest, tenths of a degree of resolution that is sufficient to resolve all the nonlinearities, or let's say the most important nonlinearities in the area, and a global model at coarser resolution. And these models are able to interact. These models are able to interact at all timescales, basically at every time step. That means our regional model, which is quite similar to the ROM system, of course of a different architecture, but not too far away, receives its open boundary conditions at every time step, and is also able to feed back to the global ocean at every time step. This has two advantages. First of all, it allows us to run lots of experiments that we couldn't do with a fully globally high-resolution model. But there's a second advantage, because it allows us to compare the standalone model with a standalone model including the nest. So a model with nest and a model without nest that is able then to isolate and highlight the importance of the Agulhas mesoscale effect on the large-scale circulation. Well, I spare you with the rest of the model details, but it's basically important that we run hindcast experiments. Hindcast experiments with prescribed atmospheric forcing at full 6-hourly daily resolution and interannual variability of the past 40 years or so. So this is just a quick, sketchy movie that is of course no proof that our model does good. Of course, we did several of the verification. It rather shows you that all the important variabilities are in place. We have, of course, the Agulhas current, which is normally very stable, but from time to time it's disturbed and shifted offshore by the Mozambique eddies and the eddies east of Madagascar. And the combination of the strong and retroflecting Agulhas current and these instabilities north make a vast range of nonlinearities in the Cape Basin, the area just east of Cape Town. And it takes a while. It takes up to the Whaleford Ridge to see isolated Agulhas rings. And this is basically the closing loop then of the global thermohaline circulation. What you see here, by the way, is the nesting. So from a technical point of view, showing you that the embedding works in a way that you see no retroflection, no reflection at the model boundaries. Now, I said we did a lot of verification, and let me show you one exemplarily, which is focusing on the Agulhas current. The Agulhas current, as you remember, is sandwiched between the eddy variability in the Mozambique channel and the Agulhas ring formation. And this is one example. It's again a cross-section over the Agulhas current. On the left, a compilation from observations from 6 or 7 ship-going observations. Harry Bryden, of course, made 1 or 2, if not 3 of them, but compiled by Lisa Beer. And on the right, you see a mean of the model, a long-term mean of the model. And in both, you see basically the typical V shape. You see the right velocity structure. You see the correct transport in the, which I will show in the next slide. And you also see some Agulhas undercurrent, not so confined to the shelf, a little bit broader, but of the correct transport. And if you look at the variability, and this is now one more synonym for the nonlinear interactions in the Agulhas current, that you see variations from 40 swirl groups up to 100 swirl groups, sometimes even more. So compared to the mean value of 77 swirl groups at that particular latitude, so you see a rather high standard deviation caused by these mesoscale instabilities, which compares very well with moorings and well, I wouldn't say long-term data, but at least continuous time series compiled by Bryden et al. Same is true for the Agulhas undercurrent. So in that respect, we had some confidence that the model was able to simulate at least most of the nonlinearity in the current region. And that, of course, makes it even more complicated. This is a zoom now at the retroflection area, and you see here the coming Natal pulses disrupting the Agulhas retroflection. The Agulhas retroflection moves back and forth, sometimes more into the Atlantic, sometimes more into the Indian Ocean, and you see the vast range of nonlinearities in the Cape Basin. This, again, is an impression how difficult it is to measure the interoceanic transport from the Indian Ocean to the Atlantic. It's not only difficult in terms of observations, because you have no continuous observations at that time resolution, but also in the model. Not even in a model you could simply integrate all the currents going west and east, because there are time lags involved in that. So only after a while, in these more angled sections, you have more or less isolated Agulhas rings that you are able to simulate. And this is the cruise track of the Good Hope program, a French-German program that runs all the way from Cape Town down to Antarctica, measuring Agulhas leakage, or at least Agulhas current variability, and then, of course, Antarctic values. Now, how did we estimate Agulhas leakage? And Agulhas leakage is, of course, not only the interoceanic transfer of mass, it's also heat and salt. And heat and salt are, of course, the important ingredients later on. Well, we did it in a Lagrangian technique. Lagrangian technique, also by a French product by University of Brest, with a software package called Ariane, where we use the full four-dimensional state of the model. So we had a three-dimensional velocity block of the model at every 5-day time steps, and we seeded virtual floats. We seeded virtual floats, and this has been done before, also by seagoing oceanographers, but of course in a limited number. In a virtual framework, in a model, you can seed millions of floats there. And every of these floats is capable of representing a certain portion of the Agulhas current. Of course, most of the floats, and here are only shown a few exemplarily trajectories, most of the floats make their way back to the Indian Ocean, but some of them ended up in the Atlantic, mostly in a spiral sense of way, and about 24% or 15 swirl of them made it in that model experiment to the Atlantic Ocean. Now, this was done in a different series highlighting the difficulty and the caution we have to put when we look at climate models, when we look at paleo models, for example. So this is now showing a series of 3 model resolutions, always with the same model, always with the same forcing, but a different horizontal resolution. First one, called Orca 05, is a 50-kilometer grid resolution. This is already high in terms of a climate model, of a global climate model. When we did the Lagrangian estimate, we had, as it is the case for most of the coupled models, we had an Agulhas leakage of up to 30 swirl. And we know from observations that this should be rather 15 swirl. And this is due to the fact that, of course, a large portion, an unrealistic large portion of the Agulhas current flows more or less directly into the Atlantic. Now, if we double the resolution up to 1/4 of a degree, we see that eddies kicks in. Eddies kick in form of Agulhas rings. In this case, at that particular resolution, far too regular, too large. But of course, the Agulhas leakage goes down because we have more now a pulsating effect. But in our series, it took up to 1/10 of a degree, and this is again the final resolution of the model that I showed earlier, to bring down the Agulhas leakage and also to bring down the standard deviation a little bit, resulting in a more wide range of Agulhas leakage that is realistic in its not too regular pathways and not too regular characteristics. Now, let me now show you the effect of that Agulhas leakage. And I will now move back to the Atlantic timescale, first showing a wave effect. We've isolated in that model context of that nested model, nested in a global perspective, 2 effects. One is the wave effect. This is a dynamical effect on the Atlantic MOC. The Agulhas rings, or Rossby waves emerging from the Agulhas region, travel and cross the Atlantic Ocean in a more about 2-year timescale, and rather than introduce and shed so-called topographic shelf waves. And for those of you who are not familiar with these 2 wave types, let me quickly introduce that. We have the Rossby waves, which are more or less an undulation around constant values of the Coriolis parameters, which are visible in the atmosphere quite prominently, but also visible in the ocean. This is an example of the tropical Pacific sea surface anomaly seen from a satellite, where you see over longitude and time positive and negative maxima going from the east to the west at a typical speed of a few years. The second effect are these Kelvin waves or topographic shelf waves. Kelvin waves act on a more or less vertical wall. Of course, this is never the case in the pure world, where you have more shelf and a shelf break. Therefore, it's a slightly modification as a shelf break. But this is basically a concentration, a piling up of water along the coast, and then a very fast movement, since we are in the southern hemisphere, a very fast movement to the north. A movement of several meters per second. And this is what is causing the time scale. So we have a more or less 2-year time scale of the Rossby waves to cross the Atlantic Ocean, but then a very quick time scale of, say, a year or so up to the North Atlantic. Now, what does that mean? And let me show you one more example how we derive the next figure. As I said before, our nesting techniques allows us to isolate the effect of the Agulhas mesoscale. And for the next figure, we compared the global model without nest, so typical coarse resolution model, where we have an Atlantic meridional overturning circulation, and we compared that with the global model, including the Agulhas mesoscale. In both cases, we looked outside of the Agulhas region. So we looked at the Agulhas region, the effect of the Agulhas region on the large scale. So in both cases, we had an Atlantic meridional overturning circulation. This is latitude from south, 30 south to 70 north, of warm water flowing to the north, convection, sinking, and deep return flow. In both cases, if we resolve the Agulhas mesoscale variability or not, we had more or less had the same circulation strengths. But if we look at the time variability, we see that the Agulhas mesoscale introduced decadal variability. So shown here is time against latitude, variations in the MOC, variations in the MOC between plus and minus 1.5 Sverdrups that are brought into the south, and these MOC anomalies can only come through the Agulhas mesoscale, that rapidly propagate to the north, so within a year or so, and rather cause a decadal variability. What you see here are not isolated Agulhas rings. Agulhas rings have a different timescale. Agulhas rings don't take decades to go to the South Atlantic. It's rather a decadal modulation of Agulhas rings or Rossby waves. Now, if we compare that, and this is again the same figure from the last slide, we knew that we have seen similar effects from the north. We know from previous work that we have these sort of Kelvin wave propagation also with northern causes. And one of the northern cause that comes into play is the convection activity in the Labrador Sea. We've seen in the morning by Monica Ryan that the convection in the Labrador Sea is also due to decadal variability, due to decadal variations. And we could also highlight and isolate that by a series of experiments, and this is shown here. This is now from north to the south, where we also see MOC anomalies on a decadal timescales emerging from the Labrador Sea, quickly propagating to the south. And of course, we asked ourselves, so what is now the relative importance of the southern effect versus the northern effect? So what we did was we compared the standard deviation. So a measure of the variability from the south, from the southern effect, which of course enters from the south, which is high which has a high variability in the south, and then slowly fades away to the North Atlantic, with the effect from the Labrador Sea convection that enters from the north at the southern entrance of the Labrador Sea, that comes in at basically the same scale, and also quickly propagates to the south and gradually fades away. And we see that in the tropical and even subtropical North Atlantic, both of these nonlinearities, both of these effects are on the same order. Now, of course, this is a wave response, and waves don't transport heat and salt. And as you may recall, thermohaline circulation means heat and salt. And so the next effect is the rather more important effect. So this is the wave effect was more an effect that disturbs and modulates the circulation signal in the North Atlantic, but the advective effect is really bringing in heat and salt from the Agulhas to the North Atlantic. As I said in the beginning, we have the wind fields shifting, and we know from observations. I know that Mathieu has a different view on that. We have a southward expansion or southward migration of the southern hemisphere westerlies that has been shown in lots of observations. We have seen observations earlier this afternoon, evidence in the Atlantic, and we also know from climate models that this should be due. And these southward migration of the westerlies causes the supergyre to increase, which is shown here. This is this so-called stream function from the global high-resolution model, from the Atlantic high-resolution model, where you see here the Atlantic, the Agulhas circulation that is connected and rather forms a complete series, a complete horizontal gyre, which is called the supergyre. Now, as the wind fields move to the south, and this is the blue series here, which is a zonal average from the 70s to the 2000s, we see a southward expansion and an increase in the southern hemisphere westerlies. As this is the case, we also see an expansion of the supergyre towards the south. And the effect is quite similar to what we've seen in the previous talk, is an increase in Agulhas leakage. Despite the fact that we have a large variation from year to year here, between say 12 to up to 22 swerdrups, we have an increase of more than 1 swerdrup per decade. And if you remember the total transport, this is a rather 25% increase in Agulhas leakage from the 70s to the 2000s. Now, of course, there are two questions. One question is, so what is happening next? What is happening in the future? Is that continuing or not? And for that, we've used a coupled climate model. A coupled climate model like Jochen Barotzke has presented that is forced by atmospheric CO2. A coupled climate model that is contrasted with a present-day experiment, where you see here the southern hemisphere westerlies and the trades and so on, contrasted with an ensemble of climate change scenarios, a scenario or an ensemble of climate change scenarios that are averaged together, where they all agree on a southward migration and intensification of the westerlies. Now, if you average the wind stress, you see here, and this is now only going from the equator down to 70 or 80 south, you see from a present day with a stippled curve, you see the southward intensification and the southward shift. Now, what we did was, of course, knowing that this climate model couldn't do every details of the global circulation, we looked at the potential effect of that. We looked at the potential effect of that by applying that anomaly function to our global high-resolution model. Anomaly function in a way that we simply subtracted the global warming minus the present-day experiments, so constantly pushing the wind fields to the south, so to get an estimate on the Agulhas leakage. And not surprising, of course, the Agulhas leakage is further increasing. The present-day experiments, this is what I've shown earlier, that of course also contains the anthropogenic climate effect, has this 25% increase. If we then run the same experiment by applying that anomaly function to constantly pushing the southern hemisphere westerlies to the south, we are entering a different state. A different state with a massively increased Agulhas leakage by up to 5 swirl groups, which tells us that climate models more or less predict, if they could, in terms of resolving the Agulhas current, that they would predict an increase, a continuous increase in Agulhas leakage. Now, what is happening now to the effect? Of course, we have to look at the timescales again. We know from Wilbert-Weyer that this is a rather decadal timescale for the water that it takes for the water of the Agulhas leakage to the north. And this is an analysis also using Lagrangian floats that are seeded in the Agulhas, like as we measured for the Agulhas leakage. And these are only showing those floats that are Agulhas leakage floats. So not those floats that go back into the Indian Ocean, but at least cross the section of the Good Hope. You see lots of recirculations in the South Atlantic, in the Southern Gyre, and eventually, and this is the majority of the water, flows the way to the north. And you have 65, more than 50, and up to 40% of the Agulhas leakage waters flowing up to 25 north, which takes about 14 years in that model perspective. So it takes 1 or 2 decades of the let's say increased Agulhas leakage waters to end in the north. What is important, of course, is that an increased Agulhas leakage is not an own measure in terms of the volume transport. It's also a measure in terms of the salt transport. And I've mentioned earlier that salt is more important because the heat is radiated to the atmosphere. And this is again another analysis by seeding virtual floats and following them on their way to the north, where we see that the increase in Agulhas leakage from the 70s to the 2000s is causing an increase, salinity increase or freshwater increase of up to 25% just due to the increased Agulhas leakage. And of course, you can start now to look at observations of Brazil, which are noisy, of course, but this is the signal you are basically hunting for. Now, and this is where it basically stops. I can't give a conclusive answer right now on the effect of the increased Agulhas leakage, but we have to keep in mind, and this is basically what Mathieu was also showing, that of course this is now a contrasting view. It's a contrasting view because for quite some time we know that there's an increased supply of fresh water by melting of Greenland, by melting of sea ice, enhancing the hydrological cycle in the north. And this is causing a threat to the North Atlantic current and the MOC, of course, and the decline of the MOC. This is one of the most driving force for the scientists. Now, this is rather the opposite view, and this is now an increased supply of saline waters, an increased, but of course delayed supply of saline waters that could potentially stabilize the MOC. But of course, I can't give a conclusive answer. You need a coupled model, you need a high-resolution model to answer those questions if the timing is correct, if the amount is comparable. So this is where it basically ends in speculation, and I would like to summarize. What I've wanted to show you, and hopefully showed you, is that we need a high-resolution model to realistically represent the Agulhas system and Agulhas leakage. And then I've isolated two different processes. One is a wave process where the nonlinearity from the Agulhas region introduces decadal variations in the MOC, quickly propagating to the northern hemisphere. The question is still open, what causes these decadal variations? Because it's not just Agulhas rings or isolated Agulhas rings. And of course, how important are these wave effects for the interpretation of North Atlantic circulation variability? Where do they manifest in the end? And the other thing is the advective process, where I've shown that the supergyre has expanded poleward due to the shift and intensification of the southern hemisphere westerlies. And of course, it's up for discussion if it's the westerlies or the trades. And I think there will be some interesting science in the future, but I think we both agreed, the previous speaker and I, that the Agulhas leakage has increased, causing an increased salt export to the North Atlantic. I would also say that climate models further project the increase. But the question then, of course, is how does the timing and strength compare to the subarctic freshening? And of course, how do other sources, the cold water route, the Southern Ocean, contribute? And so it's no surprise that there's increasing awareness of the Agulhas regime now also in the global oceanic community, with lots of observations not only in the Mozambique Channel and in the Atlantic, but also the Good Hope program, that also stimulated the establishing of a SCORE working group that emphasizes on the climatic importance of the greater Agulhas current system. And to do some advertise here, that SCORE working group is organizing a conference, a so-called AGO Chapman conference, that is taking place this year in the Western Cape in South Africa. And by showing one more last movie, I would like to stop and ask for your questions. Thank you.